This whole week we're looking at something called identities, where it's really just finding a shortcut, more or less. Often we'll have like one side of these equations. If you put in like a value of x here, which is like some value in radians, and you put it in here, you find out you get the same answer. And on this first one, it's not that big of a deal because they're both equal size. But other times you'll see like something like this. It's pretty complicated. 1 minus 2 cosine squared of x all divided by sine x cosine x. If you put a value of x into all of these and get an answer, it's the same thing if you just do tangent minus cotangent. Much simpler. Which, for calculation purposes, is nice, but if you're like a coder and you're doing computer science and making apps or making, engineering software or something like that, if yours a faster way to do the calculation, right, the right-hand side in this case, it's only 2 terms here, you would want to know what that is as opposed to trying to program something that's like a lot longer. It can have more errors, more problems with like dividing by 0. Right? So that's the whole goal for this week, is just to use these properties and find out that there's something equivalent and hopefully smaller that does the whole calculation faster. Okay? So the way we do that is just a lot of substitution. So we take anything that has like a tangent and we substitute what tangent equals into it. Right? So for this case, up here we have cotangent equals cosine over sine. So what we can do here is also put in tangent. We already know what it is. It's sine over cosine. Rise over run, right? That's all tangent is. I always want you guys to repeat that to yourself. Anytime you come across tangent, think of slope. It's asking how steep that angle is. Okay? Now, something else that's true is that the square of both sides is true, because this one is tangent squared. So if we square the left-hand side, we get tangent squared. That's the same as sine squared over cosine squared. The same thing for all of these. Secant is 1 over cosine. Well, secant squared is 1 over cosine squared. And these are all the little substitutive things we're going to use through these problems. What we're going to do is substitute one thing at a time and try to simplify the left-hand side to equal right-hand side, or the right-hand side to equal left-hand side, or substitute stuff on both sides. In the end, you just want the exact same thing on both sides. And we'll do a little bit of everything. Okay? So, same thing to the 4th power, it could be that as well. So, and this is one of those things you'll get better at doing just by, practicing. We have this, remember, Pythagorean theorem of trig, a squared plus b squared equals c squared from 7th grade. We updated in trig to cosine squared, which is the run, sine squared, which is the y, equals 1, right, which is the radius. Unit circle, that's why it's always equal to 1. Now there's 2 versions or deviations of this. If we subtract sine squared on both sides, then we'll have left over cosine squared equals 1 minus sine squared. So we can use that, meaning anytime you run into a cosine squared, we can substitute in 1 minus sine squared in its place. And I'll be showing you, like, well, how do you know what to substitute where? That's the whole skill that we're trying to build today. Same thing here, if I take this same thing and I subtract cosine squared on both sides. Well, now I know that sine squared of theta equals 1 minus cosine squared. So anywhere there's a sine squared, I can, in its place, put 1 minus cosine squared. Theta or x or whatever variable we're using. Theta is kind of like a default angle. We don't know what angle we're talking about. Often we use theta. Okay. So a few things we can do. So right away over here you see that on this first problem, you see this 1 minus cosine squared. So the first thing you can look over here and say, well, you know what? 1 minus cosine squared equals sine squared. So we can start off with that and say, well, the right-hand side equals sine squared. Let me blow this up. So this right-hand side, because of that identity, we can say this thing equals sine squared of x. So the trick is right here. Can I take tangent squared and cosine squared and simplify these by multiplying them and have it equal this? And that's the name of the game, really. We just go over here and say, well, I know tangent squared. We know that's going to be rise over run, sine. squared over cosine squared. And cosine squared is, there's nothing to simplify there, so it's just cosine squared. Actually, I should be using x right here. Sorry. It should be x, not thetas. I think those thetas. X's. There we go. And we can simply do the same thing we would do if we were working in fractions. So let's say I had, 1 over something times that something. Let's say it's not 1. I'll do 3 over 4 times 4. How would I simplify? What would I do to simplify that fraction problem? Any guesses? Yeah? Yeah, because they're the same. And cancel out means equals 1, by the way. 4 divided by 4 equals 1. We can do the same thing with trig. I have a cosine squared x on top, a cosine squared x on the bottom, and voila, I have proven my identity because I have sine squared x on the left. That's what's left over. And I have sine squared x on the right. So I am finished. So that's the goal on every problem. It's just to have the same thing on both sides. Now, I could have left the right-hand side alone and just said 1 minus cosine squared and kept it all the way the same. And then on this step, I would have said, oh, sine squared is equal to 1 minus cosine squared. And my last step would have said 1 minus cosine squared equals 1 minus cosine squared. Okay. The reason I'm saying that is that you and people around you can do these slightly different and both be correct. So if you come in tomorrow or you're talking tonight and you're saying, no, it's got to be this. No, it's got to be this. Look, it's right. No, I'm right. You both can be right. Right? Both of you are even possibly 3 different ways of doing things correct on some of these. So you have to look at every problem individually and say, okay, yeah, that also works. I did it that way. You did it this way. And that's totally fine. Okay? All right, so let's practice a few more of these. All right, so what is secant squared simplify to? All right, so we have 1 over equals, and we'll substitute in what does that simplify to. This time it is theta. So secant squared simplifies to 1 over cosine squared theta. And same thing here. Cosecant squared simplifies to 1 over sine squared theta. And we have to show somehow that all this left-hand side ends up simplifying equaling just 1. So all this stuff is going to cancel out somehow or be substituted out. So again, you have to ask yourself, do you know how to do this without all the trig? Could you do this with just numbers only? So sidebar, if I had 1 over 4, would you know how to simplify that? With just numbers, right? 1 divided by 1/4. So you might recall, you might remember it being written this way in elementary school. Right? How would you solve that problem? Keep, change, right? We keep the 1, change the multiplication, flip or change, right? Keep, which basically means, the more advanced math way of what we're doing here is we're multiplying by the reciprocal top and bottom. So what we're doing is just multiplying top and bottom by the reciprocal. If I do it that way, right? The denominator equals 1, and this is multiplication, and that's where that keep, change comes from, right? So really, what I'm doing is I'm multiplying top and bottom by the reciprocal of this. So doing these identities really helps you hone in your algebra skills. I'm sorry, I did that wrong. Bottom's 1, reciprocal. Multiplying top and bottom by the reciprocal. Alright, this one would be sine. And technically, if you're multiplying by reciprocal, the denominator is 1, you don't really need to put the over 1, right? So on the left-hand side, I did that. Right-hand side, I didn't. It's totally fine just to put it this way. Since the denominator is 1, you don't really have to put over 1. If it's something else, then yes, definitely have to put it. All right, so this shows me the denominators equal 1, right? And now on the top, I just have cosine squared times 1. Of course, it's just cosine squared. I have 1 times sine squared, which is sine squared theta. And then from above, I know that cosine squared plus sine squared equals 1. So because of this identity right here, I can substitute out this and just put 1 in its place. So my last step is just 1 equals 1. I get the same thing on both sides. So you just need to know, well, why was I able to do that? You know, I took this out right here because it's equal to this, because this identity says it's equal to 1. I'm allowed to put 1. Now, sidebar, we're not allowed to do things like solving equations here. We can't multiply both sides by something. We can't add the same thing to both sides or anything like that. We just basically have to work separately. Left side is completely disjoint, unaffiliated with the right-hand side. Our tools have to stay on one side only. So we're able to multiply top and bottom by the reciprocal. We can do some factoring even. We can use some other algebra, but we can never multiply both sides by something to cancel something out, which will come up a little bit later. All right, any clarifications, questions at this point? No? Anything that we need to talk about so far? I'm going to give you a chance to do a few of these right now. Okay. So a few strategies I've given you, and you noticed, anytime I'm not sure what to do with the next step, I put in the idea, what if it was numbers only? What would I do? And that answers my question, right? If I have the same thing top and bottom, I can cancel like I did regular fractions. Same thing here, dividing fractions. So that's always a go-to strategy of ask yourself what you do with numbers and do the same thing with trig. All right, so why don't you go ahead and try B here. Substitute something for secant squared and for tangent squared and see if you can get the both sides to be the same. So right away we can substitute 1 over secant squared for 1 over cosine squared theta. Right? And we know that, of course, tangent is rise over run, sine over cosine. And we got the plus 1. And as I put on the board earlier, if you're not sure how to start here, just ask yourself, how would you do this? Right? So what's the common denominator on the fraction problem here? 3, right? So you'd multiply top and bottom by 3 over 3. So what's the common denominator on this? Cosine squared, right? So exactly, the common denominator here was what exactly is right here on the bottom, right? That's what we multiplied top and bottom on this from, to make it equal to 1. So same identical idea here. There's your common denominator, so we're multiplying by cosine squared, top and bottom. So you see, it's not the same, but it definitely rhymes. Right? If you know how to do the steps with just regular fractions from elementary school, the same exact steps here in pre-calc math analysis, right? So because 1, cosine squared divided by cosine squared, that equals 1. Anything divided by itself equals 1. Right? So normally we'd have 2 over 3 plus 3 over 3, and this would equal 1 fraction. It'd be 2 plus 3 on top, and now it's over 3, the denominator. So we'll do the same thing here, right? That's now gone. So we have sine squared plus cosine squared all over cosine squared. Okay, so hopefully you can see the relationship between the elementary version of this and then the trig version of this, as steps are the same, but just instead of numbers we got cosines and cosine squareds, right? What's next? Yeah, let's look at previous problems. Whenever I get stuck, I look at my notes. What did I do on a previous problem? That might help me. I look up here, it's like, well, look. The last problem we just did, there's a cosine squared plus sine squared, and I substitute equal to 1. What do you know? I got well, this time it's sine squared plus cosine squared, but isn't that the same thing? Is it okay? Yeah, 2 plus 3 is the same as 3 plus 2. So you'll notice that these are written in a different order, but it's still equal to 1. So now I can substitute out the entire numerator and say that entire thing, right, equals 1 on top. And the entire bottom equals cosine squared theta, and what do you know? We are finished, because we got the same thing on both sides. You'll find often that it's a good goal to try to find a sine squared and a cosine squared, because every time you get one of each, you get to take them out and replace it with a 1. So if you're trying to make something smaller and you have a cosine, right, try to get another, or a cosine squared anyway, try to find a way to get a sine squared, because as soon as you get the other half of it, you get to substitute them both out, and it makes the problem a lot smaller and easier. Okay? And honestly, writing the numbers out and looking at what would I do with numbers and reminding yourself the basic parts of fraction adding and subtracting and reciprocals and common denominators goes a long way. Yeah. Question?
Is it that like 1 over us? Like when we put it down, always just write something down. I thought it was a fraction.
Oh, okay. Yeah. This is okay. If you want to go one more step, like now that I'm at the end of the problem, you'll notice I could have just left it at the left-hand side as secant squared. And then one more step, I could have put secant squared equals secant squared. If I never did convert it on the left-hand side, the right-hand side, I could have just done this. So again, you know, I could have either one of these as final answers. It's the same. It's the fact that both sides equal the same thing. There's just different ways of doing it. Okay, so we got to be okay with that idea. Different ways of doing it correctly. Your answers may not match perfectly. All right, good. Let's keep on moving along and jump it up a level a little bit. The hardest this is going to get is the limit of your fraction fluency. Okay? So if you feel like you can do fractions really well, that's as hard as this gets. If you think your fraction work is a little bit, you know, giving you little flashbacks to 5th grade, 6th grade of adding, subtracting fractions, you're like, no. You know, some of that comes back right now. Like but that's as hard as it gets, because the rules are as hard as fractions get. That's it. So keep that in mind. If you're getting stuck, the problem or what you're getting stuck on probably has to do with what you can do with fractions. All right, so here what we're going to do, and there's a couple ways of kind of doing this. You can say, well, can I simplify this left-hand side and try to get it to equal this? Or can I simplify the right-hand side and maybe get it equal to the left-hand side? So the whole problem I leave the left-hand side alone and try to just see what this equals. Or do I have to work with both sides, you know, kind of like I did in the last one, where I changed the left side a little bit, did more work on the right side, and they came out to be the same thing. So there's definitely different approaches, and you don't really know, honestly, which way to start when you first start learning these, because you don't have a really good idea of, like, well, which one works more often. From experience, I'll give you the, you know, suggestion. Start with the tangents and cotangents, because those all turns into sines and cosines, and maybe after simplifying all those, it just turns into the other side, which happens to be all sines and cosines. So if you have one side that's just sine and cosines, another side that has something other than that, or more than that, start on that side. So for that reason, I'm going to leave the left-hand side alone for now. Okay? And I'm just going to simplify each one of these. So tangent is, once again, sine over cosine. All right? And cotangent, cosine over sine. Right? All right. And how can those be combined? And notice how there's two fractions. The second fraction is the reciprocal of the first fraction, right? So can you write a similar problem to this with only numbers? Try that right now. Write a similar problem to this with only numbers off to the side. And ask yourself, doesn't matter what the numbers are, by the way. Use single digits just to, keep it sane. But, so you're looking at this like, I'm not sure what to do. Go back 6th grade. What would you do if it's 3 over 4 minus 4 over 3? All right? Answer that question and then apply it to the trig. So, of course, the common denominator would be just to multiply the two denominators, right? So I was going to multiply this one by 3 over 3. So whatever this denominator is right here, I just multiply top and bottom right here. Okay? Use the same thing. This time the denominator is sine of x. So over here, I'm going to multiply both of these top and bottom by sine of x. Okay, so you see how, so I said the difficulty is limited by your fraction fluency. If you can put this together and see the pattern that's going on right now, you're good. If not, you're just going to need a little review and then you'll be good. Either way, you'll be fine. And over here, of course, we have a denominator of 4, so I'm going to do that top and bottom, right? And that would give me a common denominator of 12. So I'd have 9 on top minus 16 all over 12. So same thing here. So I'd multiply, since 4 in this case is what this is, so that means the second fraction I'm multiplying by cosine of x over cosine of x. Alright. We can do a little simplifying. What is sine of x times sine of x? Sine squared of x. And what is cosine times cosine? So we have sine squared of x minus cosine squared of x. Now, I could write this step, and I could put, okay, it's over sine cosine, and this one's over sine cosine. I'm going to just put it all in one big step right here. Over sine of x, cosine of x. Now, could I write this cosine of x times sine of x? Would that be okay? Yeah. So if I put like 3 times 4 and 4 times 3 would be identical. So I could put cosine x times sine of x. That's the same thing. However, I'm kind of aware of the whole problem. I notice over here, what do you see? It's sine of x times cosine of x. So just to match where I may be going, I wrote it in this order on purpose. My goal is for the left side and the right side to match. So if that's my goal, right, I have now matched the bottoms. So it's kind of like a little benchmark or a little halfway point. Right? I got half of the problem to match. Now I need to get the tops to match. I got the bottoms to match, so they're identical. Good. Now I somehow have to get this to match this. Somehow I have to turn this whole thing, sine squared x minus cosine squared x, into this. Alright, so that's our next goal. So again, if I'm not sure what to do next, I'm looking at what my goal is. My goal is to have 2 cosine squared. I need 2 cosine squared, right? I need 2 of them. Notice how there is no sine squared here at all. But what I have so far does have a sine squared. My goal is to not have sine squared. So maybe I can substitute out sine squared for something and put something in its place, because my final answer doesn't have a sine squared. So I go back up here and ask, well, what could that possibly equal? And bada bing, sine squared equals what? 1 minus cosine squared. So I can take out the sine squared and put in 1 minus cosine squared in its place. Substitute that in. Alright. So here I have now 1 minus cosine squared from the substitution. I have the minus cosine squared on the top that was already there, all over sine of x cosine x. Okay. And what can I simplify here? Does that top simplify in any way? Yes, and that's, look where we're trying to go. We're trying to get to 1 minus 2 cosine squared. Is that what this equals? Yeah, so this is kind of like, 1 minus 1 cosine, or if you want to think of a simple problem, this is the same as 1 minus x, right? Or what does 1 minus x equal? 1 minus 2x. So 1 minus cosine squared x minus cosine squared x equals 1 minus 2 cosine squared, right? So again, knowing how it works with just variables or just numbers, the trig works identically, right? So it's not easier or harder, it's just different. As I said earlier, it just kind of rhymes. And now, both sides are identical. 2. 1, 2. Negative 2. So, I am finished. Now, you notice I didn't rewrite this all the way down. Okay? It's okay to do that if you're not going to rewrite it all the way down and it just drops all the way down. At least at the last step, still rewrite it. So again, the golden rule here is, how do I know you're finished? If I want to see a finished homework, I can look up and down your paper and I'll see a bunch of problems that have the same thing on both sides. That's what a finished problem looks like on these. Okay. Now, if you kind of want to get a little lazy and just kind of not write it every single step because you didn't change it, if you just have an equal sign here, right, but it's blank, it's assumed it's the same as the thing right above it. Right. On the extra thorough, you just rewrite this every single step. Okay, so we had to use a little bit of substitution here. We took out sine squared of x, put in 1 minus cosine squared of x. I knew to do that. The most important thing about this problem is, how did I know to choose? Why not take out cosine squared of x? Why not substitute that one? Right? Yeah, I knew my goal is to get 2 cosines, so if I took out a cosine, I'd end up with 2 sines instead of 2 cosines. So I could not finish this problem unless I looked over here and asked myself, what am I trying to get in the end? Since I knew I'm trying to get 2 cosines, I took out the sine squared, so I could get that to happen. All right, try the next one, the last one. Give it a try. You want to try it on your own, you can. If not, just work with someone around you, and we'll go over it in a little bit. So let's check this out. We have cosecant, which we know is, keep doing that, 1 over sine. We got secant, 1 over cosine. Cotangent, cosine over sine. And we got tangent, which is sine over cosine. So if you wrap all this stuff together, you kind of use what we did earlier. So how do you add these two fractions together? Okay, and it looks strikingly similar to the previous problem. So if you get stuck, honestly, go back to your notes. So we just had something like this where we had some fractions to add. We found common denominators, right? And we added them up. Same thing here. There it is. We found common denominators. Right? They had different denominators, so I multiplied the opposite fraction by top and bottom of whatever that was. So it's very similar. Not the same, obviously, but this is sine over cosine minus cosine over sine. You know, tangent minus cotangent. And this one is cotangent plus tangent. So it's basically the same problem, but positive instead of negative. So if you can spot that, you'll notice that the steps to solve are almost identical. So a good reason for using your notes on your assignments. You don't have to do the problems together and then put them away, take out your homework, and now let me figure it out. Start over. Like, no, actually use previous problems. Saves you a lot of work. So here we have cosine squared once again. And now it looks pretty much the same thing as the last problem. Now I had a choice here, you know, should I put cosine then sine or sine then cosine? And I looked at the left side. I noticed it's kind of sine then cosine, so that's why I wrote it in that order. Because I know my goal is to be exactly the same, right? And last step is identical. We did here, right? Sine squared plus cosine squared. We substitute in 1, so we get. Remember, anytime you get a sine squared and a cosine squared together, and make 1. So that ends up equaling 1. And over here, I'm just going to put it under one fraction, so they are indeed identical on both sides. Right. Yeah, if you want to make the most awful nerdy love joke ever, you can say, you're my cosine squared to my sine squared. We make 1 together. Alright, so, but just so you know, if you're trying to make something smaller, and you have a sine squared, be looking for a cosine squared. That's what shrinks it down, right? It works both ways.